yield theories for ductile materials. So these theories that we will be looking into from this point are specifically for ductile materials. They can be used for brittle materials, but they do not work always. So these theories are mainly dependent on the behavior of ductile materials. So during designing a load bearing structure using a specific material, it is important to place an upper limit for the stress value which will define the material's failure. So basically, engineers will always place an upper limit, not based on a random selection but based on calculations of the end material. So this failure is usually specified at the point where yielding is initiated, which is sigma y, and therefore for ductile material the failure is specified at that point. And then we have a buffer which can also be called as a cushion time, which will lead to ultimate stress. However, in brittle materials, this failure is specified by the point where the fracture is experienced directly. So basically it's a snap without any indication. Now, like we saw previously, we will be looking into theories of failure for ductile materials specifically that are used in general engineering practices. And the most common failure theories for ductile materials involve Tresca failure theory or maximum shear stress theory, and the second one is Haber-Henke von Mises theory or maximum distortion energy theory. So the first one we will be looking at is the maximum shear stress theory, which is also called as Tresca theory. Now, a ductile material, in which one of the simplest examples being steel, usually fails through slipping. Now this is a very interesting phenomenon. The phenomenon can be easily seen on a highly polished thin strip that is subjected to tensile loading. The edges on the slipping plane, which are visible to the surface of the tested strip, are known as Luder's lines. So if you can see on the right, we have the Luder lines on the mild steel strip. So basically, when this mild steel strip is under tension, these lines will come up and it's usually 45 degrees to the plane of the shear stress, and these lines are the main reason behind slippage. Because these lines are at an angle and there is a shear stress because of that, we need to calculate the shear stress based on the state of stress based on loading. Now the yield stress of that element is sigma y, and the maximum shear stress can be calculated from the Mohr circle as tau max is equal to sigma y by 2. So furthermore, through stress transformation, we can calculate that the shear stress acts at a 45 degree angle respective to the principal stress planes. Since the plane of shear stress falls where the Luder's lines are, the material fails by shear stress. And if we do the calculation, we will see that the shear stress acts at a 45 degree angle and will be transferred to the principal stress plane. And since this angle coincides with that of the Luder line, the material will fail by shear stress. Now Tresca proposed the maximum shear stress theory, and which is also called as Tresca yield theory, with these concepts. Coming to the definition, so regardless of the loading type, the yielding of a material is initiated once the absolute maximum shear stress reaches the value of that shear stress that results in the yielding of that structure under axial loads only. Therefore, to limit failure, it is important to ensure that the absolute maximum shear stress is lesser than or equal to sigma y by 2. Now, we know that we got this value from the Mohr circle, and in terms of plane stress, the absolute maximum shear stress can be represented in terms of principal stresses sigma 1 and sigma 2. If both the principal stresses have same sign or orientation, tensile or compressive, the failure of fracture occurs when the absolute maximum shear stress is lesser than or equal to sigma 1 by 2. However, if the two principal stresses are in opposite direction, then the failure occurs when the absolute maximum shear stress is lesser than or equal to sigma 1 minus sigma 2 divided by 2. So based on the previous two equations, we can get these mathematical formulas as our final equations in the maximum shear stress theory. With that, we'll move on to the next theory, which is maximum distortion energy theory or Huber-Henke von Mises theory. So this theory was initially given by Huber, and then it was then modified by Henke and von Mises following Huber. So a material is known to experience deformation when an external load which results in energy storage throughout the volume. Here strain energy density is defined as this stored energy per unit volume of the material. Now in case of uniaxial stresses, the strain energy can be defined as U equal to 1 by 2 into sigma E. Now we use this strain energy to figure out the derivation for Beltrami or Hayes theory. Now when we take triaxial stresses, due to contribution of each principal stress, the strain energy density can be given as U equal to 1 by 2 sigma 1 epsilon 1 plus 1 by 2 sigma 2 epsilon 2 plus 1 by 2 sigma 3 epsilon 3. And from the stress theory or from the strain energy density, the Hooke's law can also be given as U equal to 1 by 2 E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu, where mu is the Poisson's ratio, sigma 1 sigma 2 plus sigma 1 sigma 3 plus sigma 3 sigma 2. Now what we have done here is we have substituted the generalized Hooke's law equation in place of epsilon 1, epsilon 2 and epsilon 3, and then we have arrived at this solution. So this equation can be observed to be in two distinctive parts, one being energy needed for volume change and other being shape change. Here if you see, in the left hand side there is energy change which is U, and in the right hand side there is shape change. Interestingly, the energy stored in the element due to volumetric change is caused from average principal stress that causes equal principal strains. Now the remaining portion of the stress equation results in energy for shape distortion. Generally, materials do not yield under a uniform hydrostatic load or average stress. Therefore, Huber proposed that in ductile materials, yielding will be visible once the distortion energy per unit volume is more or equal to the distortion energy of the same material under tension. So from whatever Huber proposed, we can obtain an equation with that, which is sigma average, that is equal to sigma 1 plus sigma 2 plus sigma 3 by 3. Now substituting sigma average in the previous equation which we saw, we will get a modified version of the strain energy equation, which is U equal to 1 plus mu by 6E into sigma 1 minus sigma 2 the whole square plus sigma 2 minus sigma 3 the whole square plus sigma 3 minus sigma 1 the whole square. Now we know that in case of plane stress, sigma 3 is equal to 0. Sigma 3 is equal to 0 because it's a biaxial case. Therefore, substituting sigma 3 as 0 here, we get U equal to 1 plus mu by 3 into sigma 1 square minus sigma 1 into sigma 2 plus sigma 2 the whole square. So finally, for uniaxial tension, where we can take sigma 1 as sigma y and sigma 2 sigma 3 equal to 0, we will get U equal to 1 plus mu by 3e into sigma square y. So this is the simplified version of the previous equation. Now if we can see here, we can always equate sigma y square to sigma 1 square minus sigma 1 sigma 2 plus sigma 2 the whole square. Therefore, from maximum distortion energy theory, wherein U equal to Uy, we get sigma square y is equal to sigma 1 whole square minus sigma 1 sigma 2 plus sigma 2 the whole square. When we take this equation in a mathematical form, we can say that it is a equation of an ellipse. Therefore, if the material is stressed enough to have a point outside ellipse, the material will fail. Now, one thing we have to note here is that comparing the two, it can be noticed that both the theories give similar results. So because both the Tresca theory and Huber-Henke von Mises theory play in the same field region and play with nearly the same variables also, we can say that it gives similar results. And the stress magnitude from both the theories show exact same values when the principal stresses are same. But when it comes to pure shear, the theories can be observed to have a large discrepancy, which is it can be calculated that, experimental calculations says that Huber-Henke-von Mises theory gives 15% more accuracy compared to Tresca's theory. The next mode of failure criterion will be failure criterion for brittle materials. Again, we have few theories of failure in brittle materials. Now, the general theories that we use in engineering practices are maximum normal stress theory by Rankine and Mohr's failure criteria. We will be seeing only these two criteria. Now, under maximum normal stress theory by Rankine, you can see that brittle materials tend to fail suddenly under tensile loading. It undergoes fracture without showing any yielding. So basically, without giving any indication, the brittle materials tend to undergo failure. Also, the fracture is seen only after the material reaches ultimate tensile stress. Now, ultimate stress is also known as ultimate tensile strength, which is often abbreviated as UTS. Now, it is called ultimate tensile strength because it is being loaded in tension, and therefore the stress of the equivalent strength is given as ultimate tensile strength or ultimate tensile stress. And on the right side, you can see there are some failure types. So the first one is failure of brittle material in tension, and the second one is failure of brittle material in torsion. Now, if you can see in this diagram or in the drawing, which is in the right side, in brittle materials, due to torsion, there is a sudden snap. So this material doesn't undergo any kind of strain hardening, necking or anything, it just snaps. The same thing happens when it undergoes tension also. There is just a indicationless snap of the material. But when we take ductile materials, for example, if we take materials like polypropylene, it has a very long necking time and then only it fails. But like we saw earlier, for the brittle materials, after the first crack initiates, the material will break away very fast when it is in tension. Now, brittle materials also experience tensile fracture in torsional test because the plane of fractures is usually at 45 degree with respect to the shear plane. So, if you can see here, the plane of fracture has been drawn, which is at 45 degree angle, and this is where the shear force is also highest, and that is exactly where the failure occurs or the fracture occurs. Now, we can prove this with the previous theory wherein we saw Luder lines. So, Luder lines occur at 45 degree angle when there is a shear stress is given to the material. Now, with that we can confirm that when the brittle material is undergoing torsion, it fails when it reaches 45 degree. Now, it has been proven through experiments that under torsional loads, the material's overall strength is minutely affected by the presence of the associated principal compressive stress. Therefore, the stress that results in fracture during the normal tensile test is same as that needed for the material to fail under torsional loading. So, from this statement what we can understand is, when we take compressive stress, they don't really result in significant failure. It is usually the tensile load and the associated tensile stress that results in actual failure of the material. So, under tensile loading, the failure that is observed is actually the stress that results in fracture of that material system. So, therefore, the theory is primarily based on principal tensile stress, and it states that it fails when the principal tensile stress is equal or higher than the ultimate normal stress of the material that is undergoing tensile loading. Now, this ultimate normal stress of the material is defined by ultimate tensile stress because the action of compressive stress there is negligent. Now, for this theory, a chalk is a good example of a material that experiences similar failure. Thus, under plane stress, the material should satisfy modulus of sigma 1 is equal to the ultimate stress and modulus of sigma 2 is equal to ultimate stress, which is sigma ULT. Now, in the right side we can see that sigma ULT is marked in the coordinate system, which has sigma 1 and sigma 2 as its horizontal and vertical axis respectively. Now after marking minus sigma ULT and positive sigma ULT, we can build a region, and with this we can say that the material fails when the stress coordinates sigma 1 sigma 2 or sigma 1 comma sigma 2 falls on the boundary or outside of the shaded area as illustrated. Now if after calculations the coordinates of sigma 1 and sigma 2 falls on the boundary of this shaded region or outside the boundary of the shaded region, then it means that the material is undergoing failure. So this is given as the maximum normal stress theory. Next we will move on to the Mohr's failure criterion. So some specific materials have different properties under compression and tension loadings. Therefore a specific criterion is required to predict failure in similar materials, which is based on the Mohr circle and is known as Mohr's failure criterion. So to successfully apply the criterion, it is required to perform 3 tests. These 3 tests will be used to apply the criterion, which is the Mohr's failure criterion, and then find out the failure range. Now those 3 tests are uniaxial tensile test to get the ultimate tensile stress, uniaxial compressive test to get the ultimate compressive stress, and torsion test to get the ultimate shear stress. Now the Mohr circle for each of these conditions are plotted. If you can see in the right side, 3 circles are plotted and the common regions are taken out of those 3 circles. Now this is the common region that has been created, and a failure envelope is created within the common regions of the 3 circles. That is what we discussed before. And if the plane stress condition of a particular state of stress makes a tangent to the envelope or lies outside the boundary, it will result in material failure. So like how we saw in the previous mode, wherein we had a square, and if the coordinate points resulted in the boundary of the square or outside the boundary of the square, we said that it will undergo failure. Same way we have the common region here, and if the plotted line or plotted points are in tangent with the boundary of this region or falls outside of this region, then it means that the material is undergoing failure. Now the 2 materials which we saw were mostly based on stress, and we didn't come across many equations because both these criteria have to fall under a region of coordinate system, and in which we will be using the Mohr's circle to depict the failure. So with that we have come to the end of the failure theory. Now we will see some examples relating these failure theories. So we can see an example here, which is the solid steel shaft has a diameter of 1 inch and yield stress of 36 ksi. Yield stress is sigma y. Now we will have to determine whether the loading causes failure, and this we have to determine with 2 failure theories. One is the maximum shear stress theory and the second one is the maximum distortion energy theory. The first one is basically Tresca theory and the second one is the Huber theory. Okay, first is first, we will have to note down the given values. So the first value we will be noting down is P, which is the axial stress, and that is 15 kip. Next there is torsion involved, which is equal to 3.25 kip inch. We know that the diameter is equal to 1 inch, therefore radius will be equal to 0.5 inch. Now it is important to figure out the cross sectional area to get values for the force, which is stress is equal to force by area. Now for the cross sectional area, CSA, A equals pi r square, as this is a tube and cross section is a circle, which will be equal to 3.14 into 0.5 the whole square, and that will be equal to 0.79 approx inch square. Now we know that torsion loading influences torsional stress and axial loading influences axial stress. This influences axial stress. We saw about torsional loading in our previous sessions, and the torsion loading will give us torsional stress. Now, when we take sigma x, which is the axial stress or normal stress, we can say that it's going to be P by A, and that will be equal to 15 by 0.79, which is equal to, after calculation we will get 19.1 KSI. In same way for torsion, we already know the formula for torsion. So tau xy will be equal to T into C by J, where T is our value of torsion, C is the maximum length at which this torsion is happening, and here the maximum length is the radius because the torsion is happening in the surface, and for us the radius is 0.5, and J is a polar moment of inertia. We know the formula for polar moment of inertia also, even that we have seen in the session where we have talked about torsion. So by substituting these values, it's going to be 3.25, which is the torsional value, into 0.5 divided by pi by 2 into r to the power 4. We know that the value of r is 0.5. So with that, tau xy will be equal to 3.25 into 0.5 divided by pi by 2 into 0.5 the whole power 4. So tau xy will be equal to 16.55 KSI. Now, although these values are given here, if you can see here, these values are already given here, but just as a refresher, we have again gone through these equations. Now if you can see here, the axial stress is acting inwards. Because it is acting inwards, we can term this axial stress as sigma x is equal to minus 19.1 KSI. Because there is a clockwise torsional force or clockwise torque, we can say that our tau xy or our shear stress is positive. Now next we will have to figure out our principal stresses. So for our principal stresses, sigma 1, 2 is equal to sigma x plus sigma y divided by 2 plus or minus root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square. Now here we only have axial loading in the x-axis. There is no y-axis loading. So we can say that our sigma y is equal to 0. So if sigma y is equal to 0, this value is equal to be 0, and this value can also be given as 0. Sigma 1, 2 is equal to minus 19.1 by 2 root over minus 19.1 by 2 the whole square plus 16.55 the whole square. Now after simplification, we will get sigma 1 as 9.56 KSI and sigma 2 will be equal to minus 28.66 KSI. Now that we have got the values for sigma 1 and sigma 2, we can go ahead and calculate the fracture criteria. Our first criteria here will be the maximum shear stress theory. So maximum shear stress theory. So in the maximum shear stress theory, we came across few conditions. So these conditions were when sigma 1 and sigma 2 are of same signs, and sigma 1 and sigma 2 are of different signs. Now by these conditions, we can see that we have different signs in sigma 1 and sigma 2. So according to that condition, we have to satisfy modulus of sigma 1 minus sigma 2 to be lesser than equal to sigma y. And in the question or in the problem statement, it is already given that our yield stress is equal to 36 ksi. Now calculation of sigma 1 minus sigma 2 modulus should be lesser than or equal to sigma y. So substituting values for sigma 1 and sigma 2, 9.56 minus 28.66 should be lesser than or equal to 36. And after calculation, we get 38.22 less than or equal to 36. Now with this, we can say that shear failure will occur. Now for this given torsion and given load, the material cannot withstand shear failure. We should also note that shear failure is the most prominent failure than any other failure in any material. So now we'll go to the next type of failure. The next type of failure criterion is going to be our maximum distortion energy criteria. So by this criteria, the formula given was sigma 1 square minus sigma 1 into sigma 2 plus sigma 2 square should be lesser than or equal to sigma y square, wherein again sigma y is 36 ksi, and that's given. So substituting those values here, which is 9.56 the whole square minus 9.56 into minus 28.66 plus minus 28.66 the whole square should be lesser than or equal to 36. Okay, this is 36 square. So after simplification, we get a value of 1187 lesser than or equal to 1296. So here we can see that the material does not fail as it satisfies the equation. Now when we were going through the distortion energy criteria, we also saw that the distortion energy criteria has 15% better results. So we'll give distortion energy criteria has 15% better results than the maximum shear stress criteria. So with that, we can conclude that the material does not fail because usually DEC or the maximum distortion energy criteria gives us better results. So with that, we come to the end of this session, and this is the last session, which is our failure criteria. And in this session, we learnt about ductile and brittle materials. We came across a different stress strain relationship for ductile and brittle materials. We saw different types of failure yield criteria for both ductile and brittle materials separately, and these theories were based on either stress or strain theories. With this, we conclude our strength of materials course. Thank you.